Hello again. This is Calculus Early Transcendentals, and we are discussing applications of the derivative, and this is sections 4.4 on L'Hopital's rule. This is a second video on L'Hopital's rule because there are a lot of components to the rule. So just to go over what is L'Hopital's rule and calculating the limit of a function. We can use L'Hopital's rule to calculate the limit, but only if our limit of f of x over g of x goes to infinity over infinity or 0 over 0. That's when we can employ the rule, which says that the limit of f of x over g of x will equal the limit of the derivative of the top over the derivative of the bottom. So please note that that is not the quotient rule. All right, so today's topic is we're going to go over another set of indeterminate forms, and this one is the indeterminate difference of infinity minus infinity. Okay, so it's not going to be 0 always, it's not going to be infinity always, it's not going to be in negative infinity. It's about, pretty much who wins the race. Remember that this function f of x is going to infinity. Another function, g of x, is moving towards infinity, but it's who's going to get there faster. Are they going at the same rate? Will they compromise on a finite number? Who knows? But we have to address the fact that infinity minus infinity, when we're calculating limits right at infinity there, what value does it take on? So a lot of the techniques that we use here are algebraic manipulations of the expression that we have. It's a nice paragraph, the one right before our examples. It says we try to convert the difference into a quotient and see if L'Hopital's rule applies then. We might want to rationalize our function. Let's say we had like a square root x minus a square root x plus 1 as x was going to infinity. We might want to multiply by a special version of 1 being the conjugate. Or we might want to use application or properties of logarithms like in the first example here. So it's about manipulating your expression to get to a place where you can calculate the limit and eliminate the infinity minus infinity. So let's start with the first one. So we do see if I'm going to our first approach is to substitute the value that x is approaching into our example or into our expression, and we see that that is going to the ln of infinity minus 1, take away ln of infinity plus 1, and infinity plus 1 and infinity minus 1 are still infinity, and we know from the graph of the natural log of x that as x approaches infinity, so does the ln of x. So this is going towards infinity minus infinity, which is an indeterminate form. So I'm just going to use the properties of logarithms. Remember the ln of x minus the ln of y, or b, say, or I can say y, equal to the ln of x divided by y. So I'm just going to use that property to rewrite my limit. And so I would get the limit as x approaches infinity of the ln of x minus 1 over x plus 1. ln is a continuous function, so we can put the limit on the inside, and so that's going to equal the ln of the limit as x goes to infinity of x minus 1 over x plus 1. And I see on the inside there that x minus 1 is going to infinity, x plus 1 is going to infinity, and so we have an infinity over infinity scenario, so we can employ L'Hopital's rule. So in applying L'Hopital's rule, I get, and this is a limit up here, the limit as x goes to infinity of, actually I want to keep the ln on the outside, sorry, ln of the limit as x goes to infinity of the derivative of x minus 1 is 1, the derivative of x plus 1 is 1, and we have here that this is going to the ln of 1, which is 0, and that is what our limit is. Taking a look at example B, we are taking the limit as x approaches pi from the left of cosecant x, and remind ourselves that this is 1 over sine of x. So we could rewrite that and see what happens. So the limit as x approaches pi from the left of 1 over sine x plus 1 over x minus pi, I see that that is going towards, and remember sine, looks like this, and we have pi here, and if we're coming from the left, we're coming from positive values, right? So we are going to 1 over sine pi from the positive amount, so it is going to infinity. But in coming from the left of pi, as x approaches pi from the left, we see that we've got values that are smaller than pi. So say pi over 2 minus pi is negative. So this is going to minus or 1 over 0, but that is from the minus side. And so this is going to infinity minus infinity. So we want to take a look at this expression, 1 over sine x plus 1 over x minus pi, and make a common denominator, turn it into a quotient, or into one fraction. So I'm going to do just that. And I'm going to multiply on top and bottom by x minus pi in the first fraction, so I would get x minus pi. And then multiply on top and bottom by sine of x in the second fraction, so we would get sine x, and then combine those into one fraction, so I would get sine x times x minus pi. So far, so good. And now I'm going to try to take that limit and see what I get. Approaching pi from the left, I am going to go to pi minus pi plus sine of pi. And approaching sine of pi from the left, I'm going to get sine of pi times 0, and that is going to give me 0 minus, or pi minus pi is 0, plus sine pi is 0. I do get 0 over 0, so L'Hopital's rule applies. So I'm going to apply L'Hopital's rule. So here I go with the limit as x approaches pi from the left, and the derivative of the numerator, the derivative of x is 1. The derivative of minus pi is 0. The derivative of sine is cosine. The derivative of the denominator is going to require the product rule. Unless you want to distribute, it's still going to require the product rule. So we might as well do the product rule. So remember, the product rule says the derivative of the first, so that would be cosine x, times the second, plus the first, sine x, times the derivative of the second, and the derivative of the second function is 1. And I'm going to try to take my limit again. So when I do that, I end up with 1 plus the cosine of pi over the cosine of pi times pi minus pi, which is 0, and then plus sine pi. And I end up with 1 minus 1 over 0 plus 0, and I still have L'Hopital's rule applies. Again. So we employ L'Hopital's rule again. So here I go with the derivative of this function, and I end up with the limit as, applying L'Hopital's rule, the derivative of the top is 1 plus negative sine, or the derivative of 1 is 0, and the derivative of cosine is minus sine. And down below, I need to do the product rule on that first term. Then the derivative of cosine is minus sine times the second plus the first times the derivative of the second. And then the second term, the derivative of sine x is cosine x. And so I'm going to apply x going to pi, and I'm going to take that limit. So this is going to minus sine of pi over minus sine of pi times pi minus pi plus cosine pi plus cosine pi, and that equals 0, because sine of pi is 0, over negative sine pi, that's 0, and pi minus pi is 0, so that's going to be 0, but cosine pi is minus 1, and again it's minus 1, and we get 0 over 2, no more L'Hopital's rule, we can make a determination, and our limit here is going to equal 0. Okay, let's take a look at this next one. And if I apply my limit as I approach infinity, this function is going to e to the infinity minus infinity, which is going to infinity minus infinity. So I'm going to make an algebraic manipulation here. I'm going to factor out an e to the x. And so that's what I'm going to do first. I'm going to say this is the limit as x approaches infinity of e to the x, open parentheses, 1 minus x over e to the x. Good. And we're going to see that we've got a limit of a product, and the limit of a product is the product of the limits. So this is going to be the limit as x goes to infinity of e to the x times the limit as x goes to infinity of 1 minus x over e to the x. We know that the limit of e to the x is going to infinity, but where is the second one going to? We are seeing that this is going to go to the limit of 1 is 1, and the limit of a difference is the difference of the limits. And so we see here that this one is going to infinity over infinity. So L'Hopital's rule applies there. So we're going to employ a L'Hopital's rule on this one. So we still have infinity here, but we're going to take the limit as x approaches infinity of 1, and then minus the limit as x approaches infinity of x over e to the x. And now we're going to do L'Hopital's rule on this one. So we get infinity times, and the limit of 1 is 1. And doing L'Hopital's rule here, we get the limit as x approaches infinity of the derivative of x is 1. The derivative of e to the x is e to the x. And we're going to take our limit. And in doing so, we are going to infinity times 1 minus, and this is 1 over infinity, which is going to 0. And now we have infinity times 1, and that is going to infinity. All right, so hopefully you have a couple of examples here that show you what types of algebraic manipulations you can do when you are faced with a limit that goes to an indeterminate difference of infinity minus infinity. I'm going to stop here and create another video, and that video is going to go over the final indeterminate forms, and you see that there. We're going to be talking about indeterminate powers and how to deal with them. See you in a minute.